We're here. We finally made it to the last section, 16.4. And so we're going to define Gibbs free energy. I'm going to show you how to calculate Gibbs free energy using free energies of formation and using enthalpy and entropy to calculate for delta G. You also need to be able to explain how temperature affects spontaneity and then relate standard free energy changes to equilibrium constants. So I know that that's a mouthful, but we're going to go through this one at a time. So the second law of thermodynamics, again, remember, states that all spontaneous processes, right, have a delta S of the universe that's greater than 0. And so we can use the second law of thermodynamics to predict spontaneity, right? But the second law of thermodynamics really only deals with delta S. But remember, I said that you have to consider the signs of delta H and delta S if you truly want to figure out whether a reaction is spontaneous or not, all right? And so we're going to talk about delta G and Gibbs free energy, because delta G is really going to determine whether a reaction is spontaneous or non-spontaneous. And so we're going to have to calculate delta G using the signs of delta H and S to determine whether a system is spontaneous or not. So we already know delta S of the universe, second law of thermodynamics, has to be greater than 0 in order for it to be spontaneous. So this reaction or this equation here is going to be your best friend, right? I want you to look at recitations 11 and recitations 12. Practice those over the weekend, this weekend and next weekend. But delta G is our Gibbs free energy. And we can look at delta G. The value of delta G trumps basically H and S. If the sign of delta G is negative, that's a non-spontaneous reaction, no matter what. If delta G is positive, it's going... I don't know if I said that right. If the sign of delta G is negative, you're going to have a spontaneous reaction. So a negative delta G means spontaneous. A positive delta G means non-spontaneous. So don't confuse the signs with the other ones. Negative delta G, spontaneous. Positive delta G, non-spontaneous. And so this reaction or this equation, delta G is equal to the change in delta H minus temperature in Kelvin times the change in delta S. We have to, again, consider the signs for delta S and delta H, but it's going to be delta G that determines whether your reaction is spontaneous or not. All right, so we just went through this, what the signs of delta G mean. So one thing that I want you to pay attention to with that formula or that equation is delta H. So delta H is generally larger in magnitude than delta S. So you're going to find that your delta H values are in kilojoules and that your delta S is in joules, right? So delta H is normally thousands of times larger than your delta S. So keep that in mind, because two things. You need to remember to convert when you're doing your calculations from kilojoules to joules or vice versa. You need to make sure that your units are the same. But the other thing is knowing that delta H is so much larger than delta S can help us to determine whether the sign of delta G is going to be positive or not. All right? And so we know what delta H means. We know that a negative delta H means that you have an exothermic process. We know that a positive delta S means that you have a random, right? You're increasing disorder. And so now, again, we're putting into practice what we've been going over the last two sections, which is using the signs of delta H and delta S to determine whether delta G is going to be positive or negative, because delta G is ultimately what's going to tell us whether a reaction is spontaneous or not. But we have to use the signs of delta H and delta S to help us figure that out. So, if my delta H is negative and my delta S is positive. What's my sign of delta G going to be? Well, if I have a negative delta H and I have a positive delta S, when I do negative delta H minus whatever S is going to be, we know that delta G is going to be negative as well. So delta G will be negative, and if delta G is negative, we said that it's going to be what? Spontaneous. So now let's say that we have a positive delta H and a negative delta S. A positive delta H and a negative delta S means that you're going to have a positive delta G. Why? Because remember, two negatives make a positive, and so everything on the right side of the equation is now positive, so delta G is going to be positive. And that's going to be a non-spontaneous process. Now, it gets tricky when the signs of delta H and delta S are the same. When the signs of delta H and delta S are the same, then the reaction becomes temperature dependent. Alright, so if we have a negative delta H and a negative delta S, how can we keep delta G negative? Remember, I said delta H is usually greater in magnitude than delta S. Because remember, delta H is in kilojoules, delta S is in joules. So delta H is usually at least 1,000 times larger than delta S. So how can we keep delta H larger than delta S? We want to make sure that you keep these conditions at low temperatures. Right? Because we don't want this positive S to override that negative H. And so this will be a negative delta G at low temperatures. That's sometimes a little confusing for students. So I'm going to say it one more time. If I have a negative delta H and a negative delta S, this becomes positive. And so in order for this delta G to be negative, we want to make sure that delta H remains larger than whatever S is. And so the only way we could do that is if we keep delta T small, not delta T, if we keep temperature low, right? So if the signs of delta H and delta S are negative, this reaction is only spontaneous at low temperatures. If delta H is positive and delta S is positive, we need now for this negative sign that's here to be larger than that, whatever delta H is. And so how can we make that delta S larger than delta H? At high temperatures. So if both the sign of delta H and delta S are positive, we can keep the sign of delta G negative at high temperatures. Alright? So keep in mind, if the signs of both H and S are the same, this becomes a temperature dependent reaction. And so whatever the temperature is dictates whether this reaction is spontaneous or non-spontaneous. Alright? A negative delta H and a positive delta S is always going to be spontaneous. A positive delta H and a negative delta S is always going to be non-spontaneous. These last two columns are spontaneous based on temperature, dependent on temperature. Alright, so let's just say now for those last two columns where the signs of both H and S are the same, we wanted to figure out what temperature is this reaction spontaneous or non-spontaneous. The way we figure this out is we have to set our delta G to 0. So we have our reaction, so G is equal to H minus TS, right? In order to figure out what this temperature is, what temperature that reaction is spontaneous or non-spontaneous is at. You set G to 0 and solve for T. And that's what we have here. So T is equal to delta H divided by delta S. Whatever that temperature is the temperature at which that reaction will be spontaneous. All right. So now we're going to talk a little bit about delta G naught. And I talked about this in the last video. The little naught here, that little degree symbol, basically just means you're under standard conditions. So the only difference between G and G naught is that symbol represents standard conditions. So standard conditions means that you have standard temperature, pressure, right? 298 Kelvin, 1 atmosphere. Whenever you see G naught, we're assuming that this reaction is taking place under standard conditions. When you just have G, it means that you can that reaction is taking place at any temperature or pressure. And again, pay attention to your units for H and S, because they need to be the same when you do your calculations, or it'll throw off your response. Put a big check next to that. All right, so example 16.7 in your book goes through calculating delta G for when liquid water changes to vapor. All right, so we have this reaction here. Right? And so the first thing that we have to do is we have to calculate, and before we can calculate delta G of this reaction, we have to calculate the delta H, the change in enthalpy. And so, again, delta H is equal to the sum of my products minus the sum of my reactants. Right? So delta H is going to be negative 241.82 minus a negative 286.83. And remember, the negative becomes positive. So you should have gotten a positive 40-something for this problem. I wrote that wrong, 286. All right, so for delta H, you should have gotten a positive 40-something. And to calculate delta G, we also have to figure out the change in delta S, the change in entropy. And we're using the same equation. So change in entropy is going to be final minus initial. So you're going to do your final, which is your gas, 188, minus 70, which is your liquid. You're going to plug this here, and now we can solve for delta G. All right, so you're going to take your delta S, your delta H minus T delta S, and that's going to give you your delta G. If your answer is negative, it's a spontaneous reaction. If the answer is positive, it's non-spontaneous. I keep mixing this up myself. All right, but again, the book has this, and again, I'm telling you to do recitations 11 and 12. Again, this is going through how to calculate delta G using delta G of formation. So I just showed you how to calculate delta G using delta H and delta S. You can also calculate delta G the same way we do delta H and delta S. So if I give you the delta G's of formation, right, we can calculate delta G using some standards that are already given. So delta G is the sum of your products minus the sum of delta G of your reactants. All right. And basically this is what you see here. Delta G is equal to the sum of your products minus the sum of your reactants. And don't forget to include your coefficients. If you have coefficients, you also have to include those coefficients in your calculations. But there's examples of this in recitation worksheets 11 and 12. All right. So now this brings us to calculating delta G under non-standard conditions. So most of our discussion on free energy to this point has involved the standard free energy change. So that's delta G naught, where we're calculating delta G based on standard temperatures and pressures. However, we can calculate delta G using this equation here. So we can use delta G naught, right? That's supposed to be a naught, plus RT ln Q, where T is temperature in Kelvin, R is a constant, and Q is the reaction quotient. And we all remember, we calculate Q like we do K. It's the concentration of your products over the reactants. I put this here, not so much for you to memorize for the exam, but just to start understanding some of the relationships that we're going to see in the next few slides between G and K. All right? Non-spontaneous reactions and how that affects K. K and Q. So I need you to still keep those in mind. So we focus heavily on the relationship between free energy change and the spontaneity of a reaction. We know that in order for a reaction to be spontaneous, the sign for delta G must be negative. But we also know that for a reaction to be spontaneous, K has to be greater than 1, right? Because spontaneous means that that reaction is moving toward product. And so what does that mean in terms of K? It means that your concentration of your product is going to be greater than the concentration of your reactants, right? So we have a forward moving reaction, we're going to have a K that's larger than 1. For that same spontaneous reaction where K is larger than 1, delta G has to be less than 0, right? Because we said for a spontaneous reaction, delta G has to be negative. And so here we're looking at, again, how they came up with these relationships, but these three reactions you don't need to memorize. I just want you to understand the relationship between delta G and K. And so this relationship between delta G and K holds for all equilibrium constants, as we've discussed throughout the course. So you've been learning about K from at least midterms till now, right? So everyone understands that, K and what that means in terms of equilibrium. And so here we have these three plots. And what I want you to look at with these three plots are the relationship between G and K. All right, so in plot 1, we have a plot that's in favor of product. We know it's in favor of product. Why? Because you have a negative delta G and K is greater than 1. Right? So this reaction is, the reaction progress is moving towards the products. In the second one, we have a non-spontaneous reaction. We know it's non-spontaneous because delta G is greater than 1 and K is less than 1, right? And so if K is less than 1, we know that we have a reaction that is going back towards the left. If we have a reaction that is at equilibrium, so it's at equilibrium, delta G is going to equal 0 and K is going to equal 1. Not 0, but 1. Because remember, at equilibrium, the concentration of the products and reactants are the same. And so K is going to equal 1. All right, so that's the relationship between G and K. You should be able to look at the sign for G and K and tell me something about the spontaneity of that reaction. We made it through chapter 16. So tomorrow, Friday in class, we're going to go through recitations 11 and 12. Bring your questions that you have. I know watching the video is difficult, but communicate to me. Email me if you need office hours. All right? Have a great day, and make sure you're watching your videos. See you soon.